All right, hello class. In this lecture, we're going to be talking about partial derivatives. Okay, so what we're going to be talking about at this time is sort of an extension of derivatives, not so much in their physics sense, right? Because we talked about that when we were looking at vector valued functions, curves in space, right? When we were looking at curves in space, we had our trajectory, and at each time we would have a velocity vector, right, which would be the derivative, and at each particular point it would tell us the direction that the object was traveling in, along with its velocity at each particular second. Okay, but what we're going to do now is instead talk about derivatives in terms of surfaces. All right, and this is going to be more of the geometric way of talking about derivatives. Because when you learn about derivatives early on, say in Cal 1, okay, what you're talking about is always, your y equals f of x. And there are two ways that you're talking about it. One is it is still velocity, right? If this function gives you the position of an object after a certain amount of time, f prime is going to be the velocity. All right, so that still holds true. But also, the derivative gives us what we would think of as the slope, right? It kind of measures the steepness, right? So measures the steepness of the curve at every particular point, right? That's what f prime gives us, basically the slope of the tangent line, okay? And which is essentially the measurement of the steepness of the curve. So that's the sort of geometric way we talk about it. Now, for a surface, here's the issue that comes about. Imagine, so here's the Calc 3 way of thinking about it. Imagine you're walking around outside, you're going for a hike, and you come across a place, say we're right here, okay, to where to the left and right you would be going uphill. All right, so that would be to the left and the right. But if you instead look forwards or backwards, you'd be going downhill. Okay, so the steepness is going to depend on the direction that you're facing in. That was not really something we had to worry about in Calculus 1, right? Because we were dealing with essentially one-dimensional problems. But here, the steepness is going to depend on the direction. Okay, so that's going to lead us into how we talk about what's going on. As far as the question becomes, what is the steepness in any particular direction? All right, so how do we find, that's the big question, is how do we find the steepness or the derivative in any direction that we want? All right. So, to begin with, we actually just focus on the positive x and y direction. Okay, so to start, so we focus on the positive x and y directions. And the reason for that, we'll get to it in the next page, but it's really the easiest ones we can start with. Okay, so let's get to it. All right, so to refresh our memory here, the derivative in the one-dimensional sense is basically just a limit, right? It's the derivative of y with respect to x, or f prime of x, is the limit as h goes to 0 of f of x plus h minus f of x all over h. So how we apply this to for a surface, okay, is maybe even a bit easier than you might expect. What we end up doing is just apply this limit to each particular variable separately. Okay, so the partial derivative for z equals f of x comma y basically isolates the x or y directions and applies the limit to only that variable. Okay, well, what in the world does that mean? So let's first start with the partial derivative, right? The partial derivative of z with respect to x. I use WRT to use with respect to, since that pops up so often. Okay, but the partial derivative of z with respect to x is, all right, so we introduce a new notation here, this sort of curly d to represent the partial derivative. Okay, and this basically means, I'll write it up here, d, or partial over partial, say x. This is the partial derivative operator. Okay, and we just use this to let everybody know that it's not a Cal 1 type case, it's a Cal 3 type case, right? That there's more than one independent variable when we have this curvy d. Okay, so the partial derivative of z with respect to x is, well, here's the other notation we can use. We can't just use prime, because if we're talking about f of x, y, we need to know what variable we're talking about. So the notation we use is a subscript x. Okay, and we can put the of x, y. I often drop that part, but it's the partial derivative of f with respect to x. And then we just take the limit as h goes to 0 of f of x plus h, comma y, minus f of x, comma y, all over h. Okay? So what this is essentially doing is just taking the derivative in the x variable. Okay? And in practice, it treats y like a constant because y is not moving. Right? So let me write some of this down. Okay? So we see that x is the only one with something changing here. So technically the y is not moving. If you think about on, say, a graph, if you think about the just going in the positive x direction, right, we'll have a delta x equals something, right? It will be positive. So let's say it's 1 here, okay? But delta y will be 0, right? Because we're not moving up or down, all right? So the partial derivative with respect to x basically takes the derivative of the x stuff while treating the y's like a constant. Now, that's the partial derivative of z with respect to x. With respect to y, it does the opposite. It takes the derivative with respect to y, but treats x like the constant. Okay, so the partial derivative of z with respect to y, same notation, partial z, partial y, or f sub y, okay, it's going to be the limit as h goes to 0 of f of x, comma, now it's the y plus h, right? So we put the plus h in the y variable, right? Minus f of x, comma, y all over h, right? So here, only the y variable is changing. So this is essentially the same here, except it's the y derivative that we're taking, and x is treated like the constant. Okay, so as I said, it takes a derivative in only the y variable and treats x as the constant, since x is not moving in this case. And so if we go up here and have some travel just in the positive y direction, our delta y here would be 1, while on delta x would be 0. Well, if delta x is 0, that means x remains constant. Okay, so this is typically how this works. You just differentiate like you normally would, except you have to be very careful about which variable you're talking about so that you know which variable to treat as a constant and which one to treat as the, well, variable. All right, so let's just look at some examples then. Okay, so let's say we have the function f of xy is equal to x cubed times y. All right, so f sub x, remember this is going to be, you take the x derivative, so you take the derivative okay, with respect to x and treat y as a constant. All right, so this is not going to be like in Calculus 1 when you were studying implicit differentiation, right? With implicit differentiation, you assumed y was in terms of x, and so here you would have to do like a product rule, and anytime you took a derivative with y, you'd have to put in a y prime. We don't have to do that here because x and y are independent of one another, right? It's z that is dependent on x and y, and these we are assuming are not dependent on one another. Okay, so what we do is, again, we're just going to differentiate this with respect to x. So the derivative of x cubed is 3x squared. And we're going to treat y like a constant. Well, y is a constant, we just leave it outside. It remains unchanged. Okay, so this will end up being just 3x squared y at the end. All right, next up will be f sub y, and in this case, this is where we take the derivative with respect to y and treat x as a constant. So what that means here is that when I go to differentiate this x cubed, that's just a constant. Okay, that could be 5 for all I care, 5 cubed. Okay, so it just comes along for the ride as x cubed, but the derivative of y with respect to y is 1. Okay, so this comes out to just be x cubed. All right, so to kind of show you what's going on, let's take a look at, I want to show on a graph let's just do the point 1, 1. Okay, at the point 1, 1, f sub x at 1, 1 is going to be 3, and f sub y at 1, 1 will be 1. Okay, so remember, this is slope in the x direction and the y direction. Okay, and it's technically the slope in the positive x direction and the positive y direction. Okay, that's going to actually make a difference when we're talking about surfaces, like what direction we're facing in. And with these partial derivatives, it's always the positive x and y directions. All right, so here I have the surface x cubed y. Okay, and here's the point 1, 1, 1. So when x and y equal 1, of course, z is also going to equal 1. Now, if we look at this from up above, if I start with the y direction, the y direction is here in the green. If we were to travel in the positive y direction, we would actually travel along this line here, right? And if I move this around, we see that that's actually traveling up the side of this really steep sort of incline here. Okay, so that's actually, turns out, that's the slope, right, that we got, a slope of 1. Okay, I started with that one because it's a little easier to visualize. Now, if we instead, right, looking straight above, travel in the positive x direction, what ends up happening is we are traveling up this incline. Okay, so that's the positive, whoops, don't want that to happen. It's kind of hard to see here, but when we travel in the positive x direction, we're traveling up and along this red curve, and there's the tangent line intersecting that curve, and we can see that that is actually a slope of 3. Okay, so that is what the partial derivative gives us at any particular point, is the steepness in that direction. Okay, at that point, right? It will increase up here, right? It'll get to be higher depending on what point you're talking about, but that is what it gives us. Okay, let's look at another example. We're going to look at f of xy equals x squared minus y to the 4th plus 10. Okay, so the partial derivative with respect to x, so remember that means we're going to differentiate x and treat y like it's a constant. Okay, so here, the derivative of x squared, 2x. Okay, when we treat y like a constant, that means its derivative is going to go to 0. Right, because it's all by itself here. Then the derivative of 10 is also 0. So this ends up being 2x. Okay. Then f sub y, this is where we differentiate with respect to y and treat the other, anything else, x's, whatever, as a constant. So, x squared, that's going to be a constant. Okay. Then the derivative of y to the 4th with respect to y is 4y cubed. And then 10, of course, is a constant. So at the end, this comes out to be negative 4y cubed. All right, so once again, let's take a look at a graph at the point 1, 1. And when we plug 1, 1 in, so f of 1, 1 is going to be 10. Right, so let's look at the point 1, 1, 10, and just to, visually see what this stuff tells us, because at 1, 1, f sub x at 1, 1 will be 2, and f sub y at 1, 1 will be negative 4. All right. All right, so here we are. Here's the surface. Here's the point 1, 1, 10. Okay, and if we look in the x direction, here we go. Yep, going in the positive x direction. So if I look straight above, here we are going in the positive x direction, and we can see that that takes us up this curve. All right, which will be, whoops, wrong one. Let's see. Yep, there we go. And there is the slope of the tangent line there, which is a positive, and it's harder to tell at this scale, but it's 2. Okay. Next up, if we go in the positive y direction, right, we'll be heading down this incline here, okay, which will then give us this. Okay, so if we compare the two tangent lines, okay, we see when we travel in the positive x direction, this one's going up, whereas here, when we're traveling in the positive y direction, it's pointing downhill, so that will be a -4. Okay. So as we can see, these types of situations where one direction is uphill and the other is downhill can happen even if there's no weirdness happening, right? Even if there's no discontinuities or weird behaviors. Okay, so let's just go to another example now. All right, so for this particular example, let's look at f of xy equals cosine of x squared y to the 5th. So when we do this, this is actually going to be chain rules, right? So when we do f sub x, all right, it's going to be, well, remember, it will be the derivative of the outside, so negative sign, with the inside left alone. Right, so let me specify here that this is the chain rule. Okay, and then we have to multiply by the derivative of the inside. Now, when we take the derivative of the inside, we're only taking the x derivative and we're leaving the y's alone, or we're treating the y's like they're constants. So the derivative of x squared will be 2x, and the derivative of y to the 5th, well, there is no derivative of y to the 5th, that's just a constant, so we'll leave that as y to the 5th. Okay, so if we simplify this down, we'll have negative 2x y to the 5th times sine of x squared comma y to the 5th. All right. Now, when we go to take the y derivative, once again, it's going to be a chain rule. However, parts of this are going to look exactly the same. The derivative of the outside is still negative sine. The inside left alone is still x squared y to the 5th. But now when we take the derivative of the inside, it's the x squared that stays the same, and then we take the derivative of y to the 5th, which will be 5y to the 4th. Okay, so when we simplify this, this will be negative 5x squared y to the 4th sine of x squared y to the 5th. Okay, so notice though that this piece in both of them, use yellow here, this part stays exactly the same. All right, so if you remember your chain rule for normal derivatives, so the derivative with respect to x of cosine of u, if you remember, your chain rule was always, okay, well, that's going to be negative sine of u times u prime. right? So that's our normal chain rule. We can change this to a partial derivative chain rule by just, instead of putting u prime, say, well, the partial derivative with respect to x of cosine u is going to be negative sine u times u sub x. Okay? It's pretty much the same thing. So that means that the partial with respect to y of cosine of u is negative sine u times u sub y. Right? So this would be the partial chain rule. Right, but the rules that we already know carry over. It's just we can't put u prime anymore. Right? We have to put just u sub x or u sub y depending on what variable it is we're talking about. All right, thinking about it in this way is going to be really helpful in certain situations, specifically something like this, right? Because if we have the square root of stuff, well, our normal derivative rule for the square root of stuff is basically the derivative of the stuff over 2 times the square root of the stuff, right? That's our typical rule, all right, for the square root of stuff. Well, if I want to move that to a partial derivative, it's the same thing, except it's the partial derivative on the top all over 2 times the square root of u. Okay? It's going to be really helpful because I don't have to go through this every single time. I just know for a fact that every one of these, f sub x, is going to be something over 2 times the square root of x squared plus 3y squared minus z squared. And the same will be true for f sub y and f sub z. Okay, so this is going to be the overall pattern. Now I just need the x derivative of the stuff here. So the x derivative, that's going to be, well, the derivative of x squared, so 2x. Okay, then here I need the y derivative. So the y derivative is just going to be 6y. And then here I just need the z derivative. So the z derivative will be negative 2z. Now, of course, these simplify, right? The 2's here cancel. The 2 here cancels with the 3. Okay, we could simplify that down, but this is the process. And I think thinking of it in this term, right, this way, makes it a lot faster to get through these versus doing each one separately and going through that thought process every single time. All right, let's look at another example. Here we're going to have f of xy is equal to x cubed times e to the xy. Okay, so when we do the x derivative, notice this is going to be a product rule, right? X cubed times e to the stuff with x in it. So this will be a product rule. Okay, because we have x something times another x something. All right, so it'll be the derivative of the first, which will be 3x squared, times the second left alone, okay, plus the first left alone, now times the derivative of the second. Now the derivative of the second, derivative of e to the stuff is always itself times the derivative of the exponent. Well, the derivative of the stuff here, remember, this is going to be just an x derivative, and we're treating y like a constant, so the derivative of x is 1, and then y is a constant, so it stays. Okay, so simplified down, this is going to be 3x squared e to the xy plus x cubed y e to the xy. And from here we could factor or simplify in other ways, but this is the important part. Okay? Now, when we do the derivative of y, it's not going to be a product rule anymore, because the only thing sitting out here is an x cubed. And so in this case, the x cubed is going to be a constant. Okay, so if the x cubed is a constant, that means it just comes along for the ride. So all we have to do now is just differentiate the e to the stuff. So we'll have x cubed, then the derivative of e to the stuff is always just itself. And now I need to multiply by the derivative of the inside with respect to y. So the x stays the same, and then it will be multiplied by the derivative of y, which is just 1. And there we go. This comes out to be, when we simplify it down, x to the 4th e to the xy. All right, before we do any more examples, let's talk about higher order partials. So like your second derivatives, your third derivatives. That's usually a question I get when teaching this is are there second derivatives when we're talking about partials? And the answer is, of course, yes. So, for instance, if you were to take the partial of f with respect to x and differentiate it again with respect to x, right? Or you take the partial with respect to x of f and you take another partial with respect to x. Okay, we call this f sub xx. Okay. Similarly, you can do this with y. So the partial derivative with respect to y of the partial derivative with respect to y. So that's essentially you have f sub y, and you take another y derivative to get f sub y. Okay, so this is essentially what you would expect. This is essentially the concavity in the x direction. Okay, and this is the concavity in the y direction. All right. So if we go back to one of our previous examples to take a look at it, and we can see on the graph that it aligns up with what we're talking about. All right, so here, if we go back to this example, the x squared minus y to the 4th plus 10, if I take the second x derivative, right, so I take f sub x and I take another x derivative. So that would be the partial with respect to x of 2x. That will just be 2. So this implies, since it's positive, that the surface should be concave up in the x direction, right, and in the positive x direction. And if we want to do the y second derivative, right, f sub yy, well, that will be the partial derivative with respect to y of negative 4y cubed. So that will be negative 12y squared. Okay, and that's always going to be negative, or, less than or equal to 0. So this implies that the function is, or the surface is concave down in the y direction. Okay, so let's take a look at the graph to see if that actually aligns. Okay, here we are back at the graph. And yeah, in the x direction, we're concave up. All right, so it's not just that we're, going uphill, it's concave up. And if we look at it in the y direction, we're concave down. Okay, so that all works the way we would expect. What's a little tougher to wrap our heads around is the fact that we can mix these. All right, so what do I mean by that? Well, let's say if I have the partial derivative of f with respect to x, and instead of matching that derivative, I instead take the derivative of it with respect to y. Oh, well, that's going to be, say we have the partial with respect to x, and we then take a y derivative. That would be f sub xy. Okay, or we have the partial with respect to partial of f with respect to y, and we take the x derivative of it, right? So f sub y sub x. Okay, so this notation with the subscripts works, well, I guess they both work inside out, okay, except the subscripts go from left to right, whereas the operator notation goes from right to left. It's actually exactly how it works with our normal ordinary derivatives. We probably just never thought of it before, since then it's just primes going out this way or ddx's going out the other way. This is a little harder to grok, really. We will have a better way to explain what's going on in the next lesson. It basically tells us how a certain object changes in a certain direction. It's not so much concavity as it is the way a certain particular object changes. But we'll get to that. But the idea is that you're sort of mixing it up. You take an x derivative, then a y derivative, then a y derivative, and then an x derivative. Okay? We could go back to the previous example to look at these, but they're not going to be that interesting. So what I'm going to do instead is let's look at a new example and do all of the higher order partials of order 2. Okay, so we'll start with something like this. Let's say f of xy is equal to x cubed times y minus 2xy plus x squared y to the 5th. All right, so I want to start with f sub x, so that's where you just take the x derivatives. All right, so it will be 3x squared, and the y just comes along for the ride, minus 2y, because the derivative of x is just 1, and then we'll get plus 2xy to the 5th. All right, now let's shift this over and do f sub y. So now we're just taking the y derivative. So for these first two terms, the y's will just go to 1, and then we'll be left with just x cubed minus 2x. Right? Then here, it's just the y derivative of this. So it will be plus 5x squared y to the 4th. Okay? Now, I'll start to slow down a bit. So now let's take the double derivative for x, f sub x. Now we're going to take the next x derivative. Okay, so here it's going to be 6x times y. But here, the derivative of 2y with respect to x is 0. Okay, then the derivative with respect to x of 2xy to the 5th, well, that will just go to 2. And the y-5th will stay the same. Okay, so f sub xx ends up being 6xy plus 2y to the 5th. Okay, so f sub yy, well, now we're going to take this derivative with respect to y. So the x cubed part goes away. The 2x goes away. And now we'll get a derivative here. It will be plus 5x squared. So that's our constant here. So it will be left alone. And then it will be times 4y cubed. Okay, so when simplified down, it's going to be 20 x squared y cubed. All right, so now I want to start looking at the mixed derivatives, right? I want to take f sub x y. So that means I'm starting with f sub x and I'm taking the y derivative of it. Okay, this is how I write this sometimes. I actually write out the f sub x again and put a little y subscript to tell me, okay, instead of a prime, here's my y, or you could put partial y there. But now we're just going to take this derivative in terms of y. Okay, so that's going to go to 1. That's going to go to 1. So we'll have 3x squared times 1, okay, minus 2. I should probably fix these up a little bit. Okay, then the 2x will come along for the ride here, and the derivative of y to the 5th is 5y to the 4th. Okay, so when simplified out, this is going to be 3x squared minus 2 plus 10xy to the 4th. Okay, so there's f sub xy. Now, over here, I'm going to do the other direction, f sub y x. Well, that's going to take f sub y, so this guy, and then take the x derivative. So if I write it this way, it would be f sub y, which is x cubed, minus 2x plus 5x squared y to the 4th. I'm going to take this function and then differentiate it with respect to x. Okay, so x cubed, its derivative with respect to x will be 3x squared. Okay, the derivative of negative 2x will be negative 2. And then the derivative of 5x squared y to the 4th in terms of x will be 10x, and then the y to the 4th will just stay y to the 4th. That's a constant that comes along for the ride. And there we go. When we simplify this, we get 3x squared minus 2 plus 10xy to the 4th. Oh, well, look at what we have here. These are the same. Right? What we found is that f sub xy is equal to f sub yx. Is that always true? Well, yes, essentially. Okay, there's some conditions that aren't really going to affect us that much. It will really be important later on. But for most functions, most nice surfaces we have, this is actually going to be true. Okay, so this is formally detailed by kleros theorem. I think that's how you pronounce his name. So kleros theorem says that if we assume that f of xy is defined on an open set D of r squared, so that's the xy plane, and that f of xy and f sub yx are continuous throughout D, then f of xy is equal to f of yx at all points of D. So what this is basically saying is that it's possible that these two won't equal each other, but only at places where they aren't continuous. So if they're continuous on a particular set, then they'll match at all points of the set. And this is going to be true for any of our mixed partials. So what this gives us basically that, well, f of xy is equal to f of yx, but it also gives us further things, so that f sub x, x, y, we can do in any order we want. We can do f sub x, y, x, f sub y, x, x. right? So we can choose whatever order we think would be the easiest to work with. Okay? All right, so I think that's probably enough for this particular lecture video. I think you're really going to get the hang of this when you work through the homework. Okay? And that's really like practicing this. You might feel like you understand it, but it's not until you actually sit there and work through it yourself that it really starts to sink in the way that it works. Okay, so I'll leave it there, and in the next video we'll finally start to answer that question of, well, how do we take this and from it get the derivative in any direction that we want? All right, now talk to you in that particular video.